Hello, in this video I'm going to say a little bit about some of the experimental evidence for these fundamental particles and structure of matter and things like that. Now, I'm not doing a video here on CERN or other particle accelerators and colliders, because I mean that's just, there's a lot there. I'll do that in a separate video if I'm going to start discussing that. And of course, a lot of the evidence that we have nowadays, particularly for the more exotic or elusive particles, are coming from these particle accelerators. There's two things I want to talk about here. One being the alpha particle scattering experiment that Rutherford conducted, because that comes up a lot in exam questions, and it's the evidence that led to the first descriptions of atomic structure in the way that we know it nowadays. Okay, it was a primitive description, but aren't they always when you start off? So I'll say a little bit about that, and then I want to say a little bit about neutrinos as well, because they're interesting particles. So I'll just talk about those two things here. So let's start with Rutherford and his alpha particle scattering experiment. So if we go back to the end of the 19th century, early 20th century, you've got J.J. Thomson has not long discovered the electron. And he had tentatively and rather reluctantly come up with a proposed model of the atom, now knowing that we've got these more massive positive charges and these less massive negative charges. And he proposed this, what's now known as the plum pudding model, where you've got this load of positive charge with these little negative charges stuck in it, like currants in a plum pudding. So that was a suggestion. He wasn't exactly wedded with this idea, but they were a little backed into a corner because, of course, they didn't know anything about the strong interaction. So the idea of having multiple positive charges that were still relatively massive but held together by the strong interaction, that wasn't really on the table back then. So they went for this continuous positive charge with these little negative bits stuck in it. Now, Rutherford then came along and he set up this experiment. He was a supervisor with Marsden, who was also from New Zealand, like Rutherford was, and then Geiger, a German, Geiger as in Mr. Geiger counter. And they did a experiment where they fired these alpha particles, so helium nuclei, at some gold foil. So the alpha particles are all positively charged. This gold foil was made super thin, so it was just a few atoms thick. You fire the alpha particles at the gold foil, you set up detectors all the way round, which in this case was some zinc sulfide. So every time an alpha particle hit it, you got a little flash of light, so they could measure those and then see where you get the light spots. So what happens to the alpha particles as they interact with this gold foil. And they found that the vast majority of them went straight through, and you got a load of light appearing directly on the other side of the gold foil from the alpha particle source. But you'd get around about 1 in 2,000 would scatter in some fashion, and you'd get little dots appearing in other locations, and you'd get round about 1 in 10,000 would actually scatter more than 90 degrees, start coming back towards the source in some fashion. So what was all of this telling them? Well, you got two main conclusions from this. The fact that the vast majority went straight through is telling us that mostly we've got empty space here, because most of them weren't interacting in any way with the gold foil. They just went straight through. But then you've got these ones that are scattering, particularly these ones which are scattering back towards the source. So we're not just getting something which is maybe encountering, if you've got this positive charge coming in, maybe encountering a negative charge and bending around it, being attracted towards it and that changing its path. It's actually coming backwards, so it must be meeting another concentration of positive charge. And for this positive charge to deflect a relatively massive particle, we got 4 nucleons here, to deflect it back when it's being fired at it with high energy, you must have this high concentration of positive charge. It must be dense because we've got all this empty space around. So it's giving us then this this structure of an atom. We got this concentration of positive charge there. So now they can get a new description of what the atom must look like, of a small positive charge with mostly empty space around it, which happens to be where the electrons are nowadays. But it was giving us this description, this idea of a small positively charged, densely concentrated atomic nucleus. So that's what's come out of this experiment. And that, of course, then led on to people using this to set up, people like Bohr were then creating better descriptions off of this evidence and coming up with things that begin to look like the descriptions of atoms that we have nowadays. So that's the alpha scattering experiment. Now let's think about neutrinos then, these ultra elusive particles. And we've encountered these because they're fermions, they're leptons. These are partnered up with the electron, the positron, the muon, tau. All of these have got neutrinos, and we've seen them in things like beta decay. So when you get beta decay, we're getting anti-electron neutrinos emitted. For beta plus decay, we're getting electron neutrinos being emitted. So they're appearing in our standard model description, they're appearing in our beta decays and other such interactions that are associated with the weak interaction. And there was a lot of interest in neutrinos in the 80s and 90s because, it's really hard to detect them and not that much was known about them. There were a couple of concerns back then. There didn't seem to be as many neutrinos coming out of the sun as people thought there should have been. So that was a concern. And there was also a possibility that if they had enough mass, that they might solve the problem that people had back then of dark matter. Now things have moved on, talking about dark energy as well as dark matter. There wasn't discussion of dark energy back then. Everyone was focusing on dark matter. Where are we going to get this mass from? Maybe it's coming from the neutrinos. So there was a lot of talk of neutrinos back then. The issue with the neutrinos coming out of the sun and being a deficit of them, well, there ended up being a lot of description about the weak interaction, because you recall with a weak interaction, you get particles start changing flavor. That was the description that we had for these things. We have color associated with a strong interaction. We have electric charge, or what we just call charge, really, for the electromagnetic interaction. And then you have flavor for the weak interaction. So you were getting these flavor changes, which was messing things up a little bit. But the neutrinos, though, in general, they were postulated by Pauli back in the 1930s to explain the conservation of energy and momentum and spin and all this other conservation stuff in these beta decays. And then it was Fermi who called them neutrinos. The little neutral one is what that means in Italian, in early 1930s, because they didn't want it to clash. The neutron had just been discovered by Chadwick. And then they were first detected in 1942. It was Cowan. I think the other chap was, I think you pronounce it Rhines. So it was Cowan-Rhines experiment. So Cowan and Rhines, if I pronounce that right. I think that's how you spell it, Reines. And they managed to detect some neutrinos that were coming out of a nuclear reactor. It was another 20 odd years before anyone detected a naturally occurring neutrino. And this is where you need to get into very sort of limited experimental conditions. They go down into things like old gold mines. I think they did this in South Africa in the 60s when they first discovered these, because you want to get away from things like cosmic rays and other background radiation, because you're not detecting these neutrinos directly. The neutrinos, they're not charged, they're not ionizing things. So you can't detect them in the same way as you can a lot of other particles. You need to get very high energy neutrinos and then get them to cause other effects, which is why you need to be deep underground, because those other effects could be caused by, say, a cosmic ray or something else. So you want to try and strip away all of the background that you've got. because neutrinos just go through anything as if they're not there. This is what makes them really, really interesting. So the way you can go about detecting them is if you get these massive pools of water deep underground and then look for what's called Cherenkov radiation. So that's where you're getting an incoming neutrino will create something inside. If it's high enough energy, it might create an electron or a muon or something like that. That created particle then moves through the water, because the water, well, it's a dielectric, so that's it's an insulator that can be polarized. You know what water's like. You can polarize water because of the way the water molecules are set up, where you've got your hydrogens pulling the electrons away, so you get like a dipole effect with the water molecules. So you can polarize it and align all these water molecules, and then when you get something like an electron move very, very quickly through this dielectric, it starts emitting this Cherenkov radiation that can then be detected. So that's one way that these neutrinos are sort of indirectly detected. Another thing is they might set up loads of chlorine, because if you get loads of chlorine, neutrinos can change some of that chlorine into argon. So you leave it there for a while and see if you've got more argon than you expect, in which case, you know, that gives you an indication of what's going on, how many neutrinos might have passed through. But they're really, really hard to detect, and we can only really be detecting the high energy ones that make these changes happen. So if you've got lower energy ones, well, yeah, as far as I'm aware, we're not really detecting those at the moment. And that still makes things like determining the mass of neutrinos, because we've got these different types, the electron neutrino, the muon neutrino, the tau neutrino, very, very difficult. At the moment, we can say things like the sum of the masses of those three neutrinos is less than, I don't know, a millionth of the mass of an electron or something. That's how light these things are, how little mass that they've got. And they just don't really interact with things. And as I say, that's why they're interesting, because they go to and come from places that other particles just can't reach. They're like the Carlsberg of fundamental particles. They can get, if you've got a neutrino that's created in the center of the sun, they just come out of the sun as if there's nothing there. It's not like the photons, which take forever in order to work their way from the core of the sun to then come to the earth. The neutrinos just pass through it like butter. The same with if you've got stuff behind interstellar gas clouds. The neutrinos go straight through it. If we want to look at the center of our galaxy, look at the center of the Milky Way, well, if we can set up a neutrino detector that can detect these things well, then we're seeing things that otherwise we can't see, because other electromagnetic radiation, if we're looking at any of the electromagnetic radiation, we're struggling then to look at this. We might be able to look at it at the high frequency end, but neutrinos give us another view of it. This is what's going on here. We've got the same maybe with supernovae as well. So you've got a supernova, there's not much escapes that. Okay, we can see things, but we're not getting other particles that can escape a supernova. Neutrinos can. So we get these massive neutrino bursts when a supernova happens. And the volume, the number of these neutrinos that happen, even massive distances away, is just mind-boggling. Huge orders of magnitude. So they could be very, very useful in future if we get better at detecting them. So there's still a lot that's unknown about those neutrinos. So that's why I wanted to mention a little bit about them. We might not be looking at neutrinos as an answer to the fate of the universe, as people might have been thinking back in the 1990s, but there's still a lot that can be done with these, and we do have ways of detecting them. All of these different types of neutrino have been detected, and this is how we're piecing together this evidence for the standard model of particle physics. So I'll leave that there for now. Anyway, there's a couple of other things to be added in. The number of experiments that have been conducted in order to try and validate the standard model is immense. So there's only so many of them that can be mentioned, but it's a bit of background for you anyway.